So we need to find what remains to be found to derive the Einstein-Hilbert equations of motion. What remains to be found is a variation of the matter action. That's what we need. Let us assume that matter action, being generally covariant, so invariant on the general covariant transformations, is an integral of some Lagrangian density. This is Lagrangian density. For example, the action for the particle, which is proportional to the integral over ds, which is integral over square root of g mu nu z mu dot over d tau. This guy can be represented in such a form with the use of the delta function. So it's an integral over d for x square root of modulus of g times, well, in this case it's g of x, an integral over d tau delta 4 of x minus z of tau divided by square root of modulus of g of z multiplied by square root of g mu nu of z times z mu dot z nu dot. So this is just an example where Lagrangian density is this quantity. So we will encounter imaginary actions, matter actions, a little bit later. So if this guy is like this, then the variation of the matter action with respect to the metric, which is the variation of this guy over the metric, is given as follows. It's just d4x dl over dg mu nu delta g mu nu square root of modulus of g plus L times variation of the square root of the modulus. Well, this guy we already know. So using that expression, we can rewrite this as follows, as d4x square root of modulus of g dl over dg mu nu minus 1/2 of L times g mu nu times variation of g mu nu. Well, we will denote this quantity as t mu nu. Then this is by definition is equal 1/2. Well, not this quantity. This we will call as 1/2 g mu nu. 1/2 integral over d4x square root of modulus of g t mu nu delta g mu nu, where t mu nu is equal to 2dl over dg mu nu minus L g mu nu. So it is symmetric under the exchange of indices. And our goal now is to understand the physical meaning of this quantity. Who is this guy? Who is this guy? We're going to understand the physical meaning of this quantity. So to understand the physical meaning of t mu nu, let us consider the following fact. Among the variations of the metric, there are those variations which do not change the Riemann tensor. Such variations which do not change the Riemann tensor. This is the first type of variations. And there are also variations which do change the Riemann tensor. Do change the Riemann tensor. These variations are physical, these are unphysical. Well, why physical, what unphysical? Physical means that these variations of the metric, they change the space-time itself. They like curve it, change the curvature, change the distances between different points in space-time. While this variation just corresponds to the change of the reference frames, of the coordinate nets in the space-time. So this variation is unphysical. It doesn't change the space-time. It just corresponds to unphysical changes. So let us concentrate on this type of variations. Let us consider what are those. And we want to find infinitesimal form of these variations. Well, finite form of these variations is given by this equation, the transformation of the metric. The transformation of the metric is just, as we know already, is as follows. Well, this is not the metric, this is inverse metric tensor. So its variation with upper indices is as follows. dx bar mu divided by dx alpha dx beta. So we want to consider the following transformation, that x bar of mu is just x mu plus small change of the coordinate system. This is a small vector field. Then, from this formula and this formula, we observe, to the linear order in epsilon, we observe that g bar mu nu of x bar is approximately g alpha beta. So we care only about the linear order. So it's delta mu alpha plus d alpha epsilon mu delta nu beta plus, these are just Kronecker symbols, plus d beta epsilon nu. That just follows from plugging this here. So this is already g mu nu of x plus d mu epsilon mu plus d nu epsilon mu. And this is just, we denote as g mu nu of x plus d mu epsilon mu symmetrized. So this is a symmetrization of indices. This is just definition of this guy. And what remains to be done? We have to realize that this guy depends on x bar while this guy depends on x. So then g bar mu nu of x bar is just g bar mu nu of x plus epsilon, and approximately this is just g bar mu nu of x plus d alpha g bar mu nu of x times epsilon alpha. Well, then the variation, the infinitesimal variation of the metric under the coordinate, under such a coordinate transformation, which is by definition is just a difference of g bar mu nu of x minus g mu nu of x. This is just approximately, as we have found, is just d mu epsilon nu minus d alpha g mu nu epsilon alpha, which is just the covariant derivative symmetrized of epsilon nu. So now we're going to use this variation of metric, which is unphysical because it follows from the coordinate change. It doesn't let, so under such a variation, Riemann tensor doesn't change. So under this variation, the variation of the matter action, under such epsilon variations is exactly equals to 0. So this is just a trivial relation, so to say. So it doesn't lead, this fact doesn't lead, under such variations, this fact doesn't lead to equations of motion. Now we're going to use this fact to draw conclusions about the physical meaning of this quantity. So the general covariance demands the following identity, that under the infinitesimal general covariant transformations, the matter action doesn't transform. Let us see what kind of conclusions does it allow to draw. So we have integral over the space-time manifold over d4x square root of the modulus of g, t mu, and the variation of the inverse metric tensor under the infinitesimal coordinate transformations. These guys we have found. So this is nothing but 1/2 integral over d4x over the space-time manifold square root of g t mu times d mu epsilon nu symmetrized. Because this guy is symmetric under the exchange of indices, and this guy is symmetric under the exchange of indices, so we have that this is equal to the integral over mu d4x square root t mu times d mu epsilon nu without 1/2 and no symmetrization. Now we want to integrate by parts here, integrate by parts. So to do that, we represent this as a difference between two integrals, d4x square root of modulus of g, of the total derivative of t mu times epsilon nu, minus integral over space-time manifold d4x square root of g epsilon nu times d mu t mu nu. So this guy being the total derivative, so we continue this equality. This guy being the total derivative can be reduced to the integral over the boundary of the space-time manifold d sigma mu t mu nu epsilon nu. So the same kind of situation as we have encountered before in this lecture, and this remains the same. We don't change it. d4x square root of modulus of g epsilon nu times d mu t mu nu. So it is a separate interesting story to consider such coordinate transformation for which this guy doesn't vanish at the boundary. This is an interesting story and a separate exercise, etc., etc. But we are not going to discuss it in this course of lectures because we are just learning from the general theory of relativity from the very beginning. So we assume that the variations, coordinate transformations, vanish at the boundary. Coordinate transformations epsilon nu at the boundary is 0. So our variation do not change the boundary terms. So as a result, this is 0. And as a consequence of this equality, for arbitrary epsilon inside the space-time manifold, to have this 0, for this to be 0 inside the space-time manifold for any epsilon mu nu, we have to have that d mu t mu nu is equal to 0. So this equation should clarify the physical meaning of t mu nu. Because this is a covariant generalization of the following law, following from coordinate transformations. This law, in special theory of relativity, was the conservation of energy momentum tensor. So this guy is a covariant form of the conservation of so this is in Minkowski space, and this is in arbitrary curved space, or in curvilinear coordinates, the same kind of law. So we have conservation law, so to say, conservation law, following from general covariance. So this guy is nothing but energy momentum tensor of the matter under consideration. Now we're going to use this, combine all these observations to derive Einstein equations.